Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my next video in my continuing series on the Math Lovers book. Here's the 3 volumes shown. I wrote this from 2019 to 2022, and you can buy any one of these volumes or the whole set on Amazon.com. They're $30 each paperback and $9 Kindle. And I think they're a good buy and a good read. But in case you don't want to spend the money, I'm doing a lecture series on the first 2 volumes. The third volume is problems and solutions. I may do a live streaming, problem set at some point. But anyway, I'm up to section 2.8 of volume 1, which is number tricks. And today I'm going to talk about what are called cyclic numbers. So anyway, let's begin. So here's a really interesting trick. I don't know if you guys have seen this before, but let's start with this number n, which I'm calling n, equal to 142,857, or if you like, 142,857. I prefer not to put a comma in here because you'll see what I mean when I say this is a cyclic number. So what's special about this number n, 142,857? Let's try multiplying it by 2 and see what we get. Well, if we multiply n by 2, we get 2n equals 285714. And I don't know if you notice anything special about that number, but it has the exact same digits as this number we started with. Not only that, but it's what's called a cyclic permutation of the digits. So notice that 2 is the third digit of n, 28, and then after that it goes 2857. If you wrap around, you get 14. Well, that's exactly 2n. Well, that's pretty wild, huh? And you can do it for any other multiple up to 6, it turns out. I'm going to show you a little table here. So here's what you get when you multiply n, the number I'm calling n, 142,857, by any multiple k from 1 to 6. When you multiply by 2, like I just said, you get the whole thing shifted 2 spaces to the right. You get 285714. If you multiply by 3, you get it shifted again, this time just 1 space to the right. If you multiply by 4, you get this thing you started with shifted 4 spaces to the right. And if you multiply by 5, you get the thing shifted 5 spaces to the right. And if you multiply by 6, you get the whole thing shifted 3 spaces to the right. And these are all the possibilities. So we've exhausted all cyclic permutations as number 142,857. Since it has 6 digits, there's exactly 6 cyclic permutations. They're not in order. If we went in order, we'd get 1 for no shift, 3 for a shift of 1 to the right, 2 for a shift of 2 to the right, 6 for the shift of 3 to the right, 4 for a shift of 4 to the right, and 5 for a shift of 5 to the right. So what happens when we multiply by 7? Well, then we get another kind of surprise. If you multiply by 7, obviously you're not going to get another cyclic permutation because we've used them all up. But what we do get instead is we get 999999. That's a rep digit. Rep digit of 9, 6 nines. So maybe that already gives you a hint as to why this works. But pretty amazing fact, I'd say. And this is the smallest example of a cyclic number up to, I think it's something like 20 digits. I'll get to some more later. It turns out there's actually infinitely many cyclic numbers, but this is the smallest one. So now you might wonder why this trick works. Well, I'm going to explain it. And the way to see why this trick works, let's start by doing something a little bit different. Let's calculate the decimal expansion of the fraction 1/7. I don't know if you guys ever did this in grade school, but it turns out it's a repeating decimal. All rational numbers, if you compute their decimal expansion, they either repeat or they terminate. And it turns out they only terminate if all the prime divisors of the denominator are either 2 or 5. If those are the only prime divisors, possibly with powers, then the decimal terminates. But in any other case, it repeats. And it might not start repeating right away. It might start repeating after a while. It might have a bunch of digits, but then goes into a repeating pattern. I am going to go into this later in my book, but for the case of 1/7, you get this kind of nice repeating decimal, 0.142857 repeating. Well, notice that 142857 is just the number we started with. That's the cyclic number. So maybe that already gives you a hint as to why it's a cyclic number. Well, now we can do some kind of clever things with this number. Let's try multiplying it by 10. And you probably learned also in grade school, whenever you multiply a decimal by 10, you just end up shifting the whole number one space to the left. So if we calculate 10 sevenths, which is 10 times 1 seventh, or if you want to write that as a proper fraction, it's 1 and 3 sevenths. And then that turns out to be, since we're shifting everything one space to the left, now we get a 1 on the left before the decimal place. But now we get a new repeating pattern. I mean, it already starts with the same repeating pattern we had before, 42857. But we include another 1 because that's going to be the next digit, and then everything repeats again. Same repeating cycle, just expressed a little differently. And now, notice that if we subtract 1 from this number, we get the decimal expansion of 3 sevenths. And that's a 0.428571. So we get another repeating decimal with a period of 6, except this time the thing that repeats is a cyclic permutation of what we started with. So I think that kind of shows you why if you multiply 142,857 by 3, you get 428,571. I mean, if you multiply, the decimal by 3, you get the decimal repeats, but you can just look at the first period. So I think when you look at the first period, you see that since the whole decimal repeated and got shifted one space to the left, then then the same thing is true of the number 142,857 because that's the period you start with. So that proves that 3 times 142,857 is 428,571, which is a cyclic permutation of 142,857. As a matter of fact, you're shifting everything one space to the left. And we can keep going like this. Let's keep playing the same trick. So again, let's multiply 3 sevenths by 10. Now we get 30 sevenths. And if you write this as a proper fraction, you get 4 and 2 sevenths. So that's going to start with 4.285714 repeating, and we do the same trick we did last time. Subtract the floor or the integer part, and if you do that, you get 2 sevenths equals 0.285714 repeating, which means that 285714 is now we've shifted a total of 2 spaces. So and this is going to be two times. So we just proved is that 2 times 142,857 is 285714, which is the same thing as we started with, but now shifted 2 places to the left. And let's keep going. Now we multiply 2 sevenths by 10. We get 20 sevenths, which we write as a proper fraction 2 and 6 sevenths. And that's going to be 2.857142 repeating. Again, we subtracted 2, and we've just shown that 6 sevenths is 0.857142 repeating. So 857,142, that's 142,857 shifted 3 places to the left, and that's 6 times what we started with. So just a couple more steps. Let's do it again. Now we're multiplying by 10 again. We got 60 sevenths, which is now, what is that? 8 and 4 sevenths. That's 8.571428 repeating. Subtract 8, we get 4 sevenths equals 0.571428 repeating, which means that 142,857 times 4 is 571428, which is now we started with, shifted 4 places to the left. And finally, one more step. Let's multiply 4 sevenths by 10. That gives us 40 sevenths, which is 5 and 5 sevenths, and that's going to be 5.714285 repeating. Subtract 5. We get 5 sevenths equals 0.714285 repeating, which means that 714285 is just what we started with, 142,857, shifted 5 places to the left, or if you like, 1 place to the right. So now, if we did it again, we'd get back to where we started. That's what this shows. So if we multiply 5 sevenths by 10, we get 50 sevenths. That's 7 1/7. So that's 7.142857 repeating. Subtract 7. We're back to what we started with. 1/7 equals 0.142857 repeating. Kind of cool. And, 7 is the smallest. It turns out you always have to start with a prime number to see this. And not every prime number works, unfortunately. I mean, 2, 3, and 5 didn't work. We shouldn't expect 2 and 5 to work because, like I said, those give you terminating decimals. But 3 doesn't work either. If you do tell you 1/3, you get 0.3 repeating. That has a period of 1. That one doesn't work. And most of the primes don't work. 7 is the smallest one which does. These are called cyclic primes, by the way. And in this table, I have a list of all the cyclic primes up to 100. And it looks like there's 8 of them. There's infinitely many cyclic primes. Not every prime is a cyclic prime, but I think a finite proportion of them are. I'm not going to go into that. That's a pretty deep number theory result. But this table lists the first 8 cyclic numbers. The cyclic primes are on the left, and the cyclic numbers they give rise to are on the right. But I think 142857 is really special compared to all these other ones. For one thing, they're all unique digits. I don't think that's true for any of the other ones. There are repeated digits. I mean, they still have the same cyclic property. Another problem with these other numbers, notice they all start with 0. And you have to start with that 0 because otherwise this cyclic trick doesn't work. For instance, 17. What do you get for 17? 0.5882352911767. You can shift that one, but you can't get rid of the 0 because if you got rid of the 0, it wouldn't work. So that's why all these other ones start with 0. And if you went beyond 100, they'd start with 2 zeros. I think if you took a cyclic prime between 100 and 1,000, it would have to start with 2 zeros. Between 1,000 and 10,000, we have to start with 3 zeros, and so on. So, you know, they're all cyclic numbers. They're just not. I don't think they're quite as nice as 7. 7 the smallest example. So anyway, that concludes my video for tonight on cyclic numbers. And thank you for watching. And long live math. And I'll see you guys next time.